So let's begin. So the very first thing you want to do is, in this particular equation, since we have our value of inductance in henries, we can find out what our value of inductance is. So the very first thing, find out what our capacitive reactance is, since we have our inductance. And to find our capacitive reactance, we would say, okay, well, XC equals the reciprocal of 1 over 2 pi FC. And if you do that, so 1 over 2 times pi times the frequency of 60 hertz times the capacitance of 0.3 henries, you get 132.63. 132.63. Sorry, I should have done that in blue. My apologies. So 132.63 ohms. Sorry, I'm doing X, not 0.3 microfarad, 20 microfarad. Sorry. So it's, yeah, I'm doing capacitance. I looked at 0.3 henries. That's our inductance for our inductance calculation. So 2 times pi times C being 20 microfarad, or 20 times 10 to the negative 6 gives me 132.63. So I'll put that right there, 132.63 ohms. All right. Okay, on to the next thing. We can find our inductive reactance. Now we can do this one. So the next thing here, we can find our inductive reactance, or reactance inductive, and that would be 2 pi FL equals 2 pi FL. So 2 times pi times frequency times 0.3 henries, I get 113.1. 113.1, so I can put that here. All right. And now what we want to do is we want to go, okay, you know, when we're drawing these things out and we look at it from a phasor standpoint, we go, well, my XL, we always will, XL is leading and XC is lagging. And, you know, this would be resistance. That would also be amperage, right? So we can find out what our total capacity, total reactance is in this circuit. So our total reactance, X for reactance, T for total. So in order to find our total reactance, well, I could say, well, my inductive reactance is 113.1, right? So I can put an arrow like that. And I can put my capacitive reactance down here, which is 132.63. So I can put an arrow down like that. And as we can see that these vectors are opposing each other, so we just subtract the two. So I would say that my total inductance would be equal to my capacitive, my total reactance would be equal to my capacitive reactance minus my inductive reactance, as they're 180 degrees out of phase with each other. So my total value would be 132.63 minus 113.1. So my total reactance in the circuit is going to be 19.53 ohms. That's my total value of reactance. So I could write in here, I could write that number, 19.53, and we know it's slightly more capacitive. My capacitive reactance is a little bit higher than my inductive reactance. So if I was to graph that, I could graph it sort of like this, and then say, okay, well, that's XT, and that XT equals 19.53, right? So then I could go, okay, well, let's go like this. So that would be, oops, didn't take. So I could draw sort of like this, like if I'm to, you know, take a look, so around there like that, right? And then, you know, that's sort of what I'm left with. And and it's primarily capacitive. So I would say, well, my total reactance capacitive would be 19.53. And that's how I've drawn the triangles. Now, doing this, yourself, you probably wouldn't draw the triangles until you knew if you were more capacitive, if you were more inductive, and then you would change those triangles to accurately reflect, what it is you're seeing within that circuit. So I have a slightly capacitive circuit here. So next thing, let's take a look at, let's find our total impedance here. So step number 4, our total impedance, or Z, would be equal to my resistance squared times my reactance total, which happens to be capacitive, squared. Right? So the capacitance being higher is somewhat more predominant in the circuit based on the information that we see here. So we want to find our total value of impedance, which is the square root of the square of resistance times the total capacitance. So total reactance, which happens to be capacitive. So if I do that, I end up with 53.678 ohms for total impedance. $53.678. And if we're to look at this here, when we had our total reactance, we could also write that in here. We could say, okay, well, that is my total reactance capacitive. And I'm just going to write that down here just so we have our information being filled out here. And then we've just solved for Z, which is 53.678 ohms. So we've got that. So we've got that done. So now we can actually find a couple other things. We can find our power factor and our angle theta. So step number 5, we can find our power factor. And then out of our power factor, we can find our angle theta. So power factor is equal to, we would say, 50 over 53.68, right? Total power factor would be true power, or in this particular case, we're using resistance here. So R over Z. So 50 divided by 53.678. And I get a power factor of 93%, which is pretty decent. In power factor correction, we shoot for around 95%. Anything lower than 93%, then we really have to be able to do something in order to correct this. So in this particular case, if we wanted to correct it, we try to correct with increasing our inductive reactance by a small amount. Or if we can, decreasing our capacitive reactance by a small amount to get it a little bit closer to the value that we need to get 95% or close to 95% for power factor.